Okay, so welcome everybody to our first talk of today's Quasiworld seminar. So the speaker is Mariusz Urbanski, and he will tell us about hyperbolic dimension gap for entire functions. So please, Mariusz.
Yes, thank you very much, Mario. Thank you very much, all of you, for invitation to speak for this seminar. It's my pleasure to do this. So I will be speaking about actually meromorphic functions and Julia sets for these meromorphic functions and some significant sets, and trying to relate, say something about relations between Hausdorff dimensions of these various sets. So this is the joint work with Volker Mayer. The paper, I think, either already appeared or is going to appear in proceedings of American Mathematical Society. So, okay, so let's start with really basics. If we have a meromorphic function, then I think actually all of you probably know, certainly know that the Julia set, that the Fatou set consists of those points around you have which admit some neighborhood such that the iterates for normal family, and then the Julia set is the Julia set is complement of the set. So actually, from the very definition, the Fatou set is open, Julia set is closed. Actually, Julia set is not empty, it is perfect, and both sets are invariant. The Fatou set is backward invariant. Julia set is forward invariant for infinite for transcendental functions. This is a little bit more subtle about the equalities than for rational functions because of the presence of infinite and some other things. But at least we have forward invariant Julia set, and we can see look at its at the iterate, the dynamical system. So I'll be speaking about some special class of functions. So let me first introduce one notion, which is the singular set. So if you have a meromorphic function, then you look at those points such that for which there is no neighborhood, such that the pullback is actually a covering map. For example, 0 is a singular value, is an asymptotic value for the map E to Z, and 1 is singular value, and 1 is singular value, so a critical value for the map Z squared goes to Z squared plus 1. And these are essentially the only two possibilities, kinds of singularities where may occur. Formal definition for asymptotic value is that you have a curve tending to infinity, such that along this curve, the values of the function go to this point W. And critical value, these are really very familiar, the points that are images of critical points. And I want to speak about Yeremienko-Lubitsch class B, which was introduced by Yeremienko-Lubitsch in 1992 as defined of sets of functions that the singular set, the set of finite, is bounded. For example, all exponential functions are of this form, and many all natural functions are of this form. And there is even more special spacer class for which the set of singular values is finite. And this is also these functions which I mentioned. Okay, actually, a lot of work has been done already for this class of functions. Is quite often considered in the theory of iterates of meromorphic functions. So you know that Julia set exhibits some kind of chaotic the map restricted to Julia set is kind of chaotic, is random, is actually unstable in the sense of Lyapunov, and the sets which its subsets that share more of this property are really unstable are hyperbolic sets. So such set is called hyperbolic if and only if it is compact, in particular bounded, forward invariant, and it's expanding in a natural way, such that if you iterate points, then the derivatives along the orbit grow exponentially fast. And then the Julia set, this set is contained in the Julia set. And Hausdorff dimension, hyperbolic Hausdorff dimension, is defined to be the supremum. You look at all such hyperbolic sets and take the supremum of Hausdorff dimensions. So then this is one way of looking at this expanding behavior. Another way is to look at Euclidean radial or conical Julia sets. So these are the points such that the forward the points that do not escape to infinity. So the moduli stay bounded. Okay, some on subsequence they go to infinity, but stay on subsequence stay in finite in bounded region. And if you take the pullbacks, then they are actually the inverse branches on these Euclidean balls are well defined, so that this is conformal homeomorphism. And they are called radial or conical because actually of some similar characterization of radial or conical points for Kleinian groups. So another definition is the set of spherical points, which is the set of points for which also we have conformal pullbacks, but now on the spherical balls. Okay, and these sets, both radial and Julia set, both radial Julia sets, Euclidean and spherical, are dynamically significant for many reasons. One simple reason is that every actually Borel probability invariant measure, it should be invariant measure, is supported on the Julia set. So measure of such sets is equal to 1, and this is simply because of the Poincaré's recurrent theorem. Okay, so actually that set, the set of escaping points, is also very much studied in this theory, but this is kind of a different species. Okay, so further definition, if we have I recall if we have a metric space and a Borel probability measure, then its Hausdorff dimension is obtained by looking at the infimum of Hausdorff dimensions of sets of full measure. And in the dynamical context, actually it can be for defined this dynamical dimension really for any dynamical system, but this is Hausdorff dimension of Hausdorff dimension of measures that are invariant and are hyperbolic in some sense. In the context of meromorphic function, this hyperbolicity requires that Lyapunov exponent is positive, or what is really equivalent that the Kolmogorov-Sinai entropy is positive because actually of Ruel's inequality, which holds in this context. So so now there's a theorem which has long history, and probably the final, let's see, the final form was really written in the paper, a joint paper with Tushar Das, Lior Fishman, David Simmons, and in 2018, and it says that if you have meromorphic functions, then all these characteristics of the Julia set, fractal characteristics, so hyperbolic dimension, hyperbolic hyperbolic dimension, Hausdorff dimension of of Euclidean conical points or spherical points is equal to the dynamical dimension, and it is less than or equal. It is less than or equal, of course, than Hausdorff dimension of the Julia set. So now the sets, the spherical radial points were introduced, I think, in my paper with Anna Zdunik in 2003 in the context of exponential functions. Here lambda is a fixed number, not zero, and to iterate this one, the spherical radial set was introduced in by Lasserempe in 2009, and then actually also by his collaborators, later paper studied. For rational functions, these sets were actually introduced, I think, at least implicitly in Michael Lubitsch's paper in 1987, actually my paper in 1994, with almost complete proofs in the context for rational functions in the paper with Manfred Denker in 1991. And we actually proved it also with Janina Kotus in 2023, where there was one additional, for elliptic functions, where there was one additional characteristic, which is the minimal exponent of possible conformal measures. This is, and now, so this the question is, what is actually the relation between this number S of f equal to all of them and the Hausdorff dimension of the Julia set? So how well the Julia set is actually approximated or exhausted by hyperbolic behavior. And what turns out? Firstly, okay, let me bring the following definition. So if we have a rational function, then this function is called expanding or hyperbolic if and only if the whole Julia set is hyperbolic. So then, in particular, Julia set is equal to the set of radial points, and we are in the good situation. And then, obviously, this number, so all these numbers, including the Hausdorff dimension, are equal. And okay, we know that all the polynomials z goes to z to the power d plus c with c of sufficiently small moduli hyperbolic functions form an open set and are conjecture to form actually a dense set, which is, we know, true for many significant subclasses of rational functions and polynomials. Another characterization of hyperbolicity or being expanding is purely topological, namely that the Julia set should be in the intersected with the forward orbit of postcritical set is empty. So the Julia set never approaches this set. And then if this intersection is empty, then then now the question, let me discuss some cases where this Hausdorff dimension holds. So for hyperbolic rational functions, actually by definition, because then the Julia set is just the hyperbolic set. For parabolic rational functions, which are defined as those rational functions that it could be many definitions, that are expanding, but that are expansive, but not expanding with respect to the ordinary metric. So, or equivalently, they are such functions that the that the orbit of critical points is disjoint from the Julia set, but the closure of orbit touches the Julia set. And another definition which justifies the name parabolic is that they are expansive but have irrationally indifferent periodic points. Then there are subhyperbolic rational functions, those for which the post-critical set is hyperbolic, and this also holds, and even no recurrent rational functions. These are such functions that the point C actually, and no critical point C comes back to itself, or comes back to itself. Finally, so-called topological Cole-Ekman rational functions, or functions with the exponential shrinking property, which basically means that you have some expanding along the orbit of critical values, or if equivalently, if you take inverse pullbacks of sufficiently small bores, then the diameters decrease exponentially fast. There are many classes of polynomials, and also for many classes of elliptic functions. And let's see. So now, okay, for rational functions, hyperbolicity, this being expanding and being hyperbolic in the sense that this intersection is empty, which is topological, are equivalent. This is no longer true for meromorphic functions. Okay, for meromorphic functions, therefore, there are several definitions. So you look at the P of F is just the closure of the forward orbit of singular values, and it is called hyperbolic if this set is bounded and disjoint from the Julia set. And it is called E-hyperbolic, or hyperbolic in an Euclidean way, if this post-critical set and its Euclidean distance to the Julia set is positive, and eventually it is called expanding if this just exponential growth along the points in the Julia set holds. So now, okay, any hyperbolic function is class B. Any hyperbolic function is E-hyperbolic, but not conversely. So this function f of z equals 2 minus log 2 plus 2z minus e to z is E-hyperbolic, but it has so-called Baker domain, and therefore it cannot be in class B. It is proved. It's not difficult to see that class B does not allow Baker domains. The function f of z equals z minus tangent of z is hyperbolic but not expanding. The Fatou functions, one of the examples of Fatou functions, f of z minus equals z minus logarithm of c plus e2 minus z is not hyperbolic, but it is E-hyperbolic and expanding for all c between 0 and e to the power minus 3. So then under some hypotheses, not so easy, the expanding property follows from E-hyperbolicity. So for meromorphic functions, this is really different. All these properties somehow split. And so I think the first examples of the case where these, say, dynamical dimensions, dynamical fractal invariants of the Julia set are smaller than Hausdorff dimension of the Julia set, were provided somehow implicitly in Gwyneth-Stallard paper 1999, and explicitly in my paper with Anna Zdunik in 2003, we did it for very simple examples, namely for exponential functions, whenever this function is hyperbolic, so it has actually attracting periodic cycle. This holds, for example, for each these functions f lambda of z equals lambda e to z, whenever lambda is already in the interval 0 between 0 and 1 over e, but for many more. So all these functions are actually hyperbolic and expanding in any of the senses I mentioned. So they are really good, both scalars and this exponential functions. So for rational functions, the issue was more subtle, and I think the first examples of rational functions for which the dynamical fractal characterizations of the Julia set are smaller than the Hausdorff dimension of the Julia set was provided by Arthur Avila and Michael Lubitsch in 2008 and then actually 2022, and okay, for some Feigenbaum maps. But for these examples, we have always that Hausdorff dimension of the Julia set is equal to 2. Okay, this here, just by the way, for rational functions, this for exponential function, this dimension of the Hausdorff dimension is 2. This is Kurz-Macmillan results already from 1985. So Avila and Lubitsch also write that for polynomials whose Hausdorff dimension is smaller than 2, one should expect or one should have that all these characterizations are equal to Hausdorff dimension of J of f. I think the problem is not settled for rational functions, but okay, for meromorphic functions, we proved with Volker Mayer the following result in 2023. So there exist e-hyperbolic expanding entire functions in the Riemann Lubitsch class B for which hyperbolic dimension, so this number S of f, this all is strictly less than Hausdorff dimension of the Julia set, and this one is less than 2. So there is this so to speak dimension gap, meaning this inequality holds, and Hausdorff dimension of the Julia set is less than 2. Okay, so to prove this theorem, to get such result, we need some good candidates of functions for which Hausdorff dimension is strictly less than 2 at the first place. And actually, Gwyneth Stallard, in a series of her papers through 1990s, provided several or families of functions with these properties. Okay, so she did quite nice work on good estimates of Hausdorff dimensions and actually computing them. And let's see. Okay, so for us, the particular family which she defined was given. Okay, I will come back more to this definition. When you take such a region open in the right half plane, and you integrate along the boundary, along the clockwise direction, and okay, and then you can extend for z in the complement of the closure of G, and then you can extend by analytic continuation. I will explain what it means later on for z, for all z actually in C, not only in closure, but for all z in C. And okay, the whole idea will be then that this function is actually close to the function, okay, let's see, f of z, which is much simpler, like a model function, e raised to the power logarithm of z raised to the power 1 plus p for z in this region, and which is actually, and is bounded, this function e of z is bounded elsewhere. So the whole actual idea will be to play between e of z and f of z, which is defined in the region, such region G. So okay, so for this we consider here the families of function where you shift the function el of z and you shift the function f, and then Guinev proved in 2000 that all these functions for L belonging to C actually are in the Yeremienko-Lubitsch class B, and moreover, if L is large enough, depending on P, then Hausdorff dimension of the Julia set of the function EL is given by such a simple algebraic formula 1 plus 1 over 1 plus p, and this number is smaller than 2. So our goal is to show that if we actually fix a p, then the limit of Hausdorff dimension of the sets of the functions EL will be equal to 1. So this means that for some moment on, it will be certainly less than the number 1 plus 1 over p, and we will have a dimensional gap, and the Hausdorff dimension of the Julia set will be less than 2. And this will make actually the proof. Okay? So we will not calculate, will not give exact formula for what is this hyperbolic dimension, but we are able to show that the limit is equal to 1, and this will suffice. So okay, so let's start with some more specific definition. So let's generalize a little bit the set G with kappa. Actually, for us, kappa will be really always greater than or equal to 1. And then let's look at this domains Gx0, moving from x0, which is originally was free, towards right. So this the domains Gn are smaller and smaller, and by the it should be z in, not g, and by the Cauchy's integral formula, this integral is 0, and therefore still for z in not in closure of G, we have equality, this equality, and this equality actually allows us to extend the original formula to the complement of the closure of n plus 1, and so eventually to the whole of C. And then now, if one consider any such a point in the complement of the closure of Gn plus 1, then again, residual theorem tells us that first of all, this function is the integral over the boundary of Gn plus 1. Then the sum of the integrals over the boundaries. And the first integral, this is actually because again of Cauchy's theorem, this is the function f of z. So the function f of z, I recall, is the function which is here. And then, okay, so this gives us that the difference is just this function, and we will actually, this permits us, actually permitted Guinev-Stallard to relate the function e of z and f of z. And here are the facts about these functions that really are taken from Guinev's paper. So if you have the region D is large enough, then the function of Z in its complement is uniformly bounded. In this region, E of Z and F of Z are well comparable along with the derivatives, and E of Z is this integral for Z not in G of D, and on the other hand, if in G of D we have such an equality, and the absolute value of F of Z is governed by this function. So armed with this estimates, we can now prove the actual theorem such that the singular values, actually it follows from the singular points of the function f are contained in such a disk. So this is the disk centered at 0 of radius r0/2, and both these regions are simply connected unbounded domains in C, and these regions are these inverse images are contained in D. So now, why is this important? This is important because if we have okay, I recall these definitions, then actually Krzysztof Barański implicitly in 2007 and Lasarempe, I think explicitly in 2009, 2011, 2019, and some other of his collaborators called that if you have a meromorphic function such that this set is bounded, okay, this actually is, okay, this itself implies that the function is in the B class, and the complement is invariant. Okay, and if you take the inverse image, then its closure is contained in the disk. So then the function is called of disjoint type. And then for this function, immediately from this definition, the forward orbit of delta r of this disk is contained in itself. So the Fatou set is contained in this one. So the Julia set must be contained in its complement, and post-critical set, these are all iterates of this set, are contained in delta R. And the fact about this jointness type is actually the strongest type of hyperbolicity and expanding, namely any entire function, or actually is this joint of this joint type is hyperbolic, and it is also expanding. And so for us, okay, this is some kind of lots of formulas. If you shift these sets and look at such inverse images, then okay, what it boils down is that we have again these inequalities, and this is such inclusions, and this eventually means that the functions FL and EL are for large parameters of this joint type. So, okay, hyperbolic, expanding, and the Julia sets are contained in the external disk of radius r, and this disk is invariant under the maps, under the inverse images. And okay, so our goal is now to really to determine the hyperbolic dimension, actually to estimate the hyperbolic dimension of these functions EL, and this can be done by employing the methods okay, of thermodynamic formalism. So now the hyperbolic dimension is in such context, especially for functions of this joint type, given as the zero of the appropriately defined topological pressure function. The formula, which ultimately goes back to the Rufus-Bowen work in 1980s on quasi-Fuchsian groups, and has since then obtained many various versions, generalization, extensions. In the present context, this such theory for meromorphic functions was ultimately developed in one of my papers with Volker Mayer. So let's see. So note this. Okay, so now let's speak a little bit about this thermodynamic formalism. Note this external invariant set is backward invariant. So all actually inverse branches and are well defined on locally. And okay, this will permit us to speak about this operator. So, so we will be particularly interested of these two kind of functions. G is equal either this model function FL or the functions we are really after EL. And we look at actually logarithmic derivative, or you can, which is G prime defined with respect, which is defined in that way. This is okay. This is like taking for the Riemannian metric, where you take Riemannian metric and divide by the modulus of Z. So this is like singular change of variables, but it does not change the Hausdorff dimension. And then for t equals 0, we formally define the transfer operator of the map G by such a formula. Okay, you look at all inverse branches, okay, which are well defined because, and you look at the derivative raised to the power minus t h of z for every w in this external disk of radius r. This formal definition, I do not claim at the moment that this series converges, but this is well defined. However, okay, we first of all just want to find for which parameters t bigger than 0, the following two properties hold. Namely, that this series converges, and moreover, that you take the function identically equal to 1, then its supremum norm is bounded. So this permits me to consider this operator LGT acting on bounded continuous functions defined on such disk. It will be then preserved. Okay, and then we can speak about spectral properties of this operator. And the second property, which is also crucial for us here, is that if you take with w to infinity, then actually the Perron-Frobenius operator evaluated at 1 converges to 0. So then if we have this property, if this property is satisfied, then actually, okay, section 8 from the paper of Volker Mayer, we can develop the thermodynamic formalism in a similar way with all its application in the paper, especially the Bowen's formula holds, which relates to Hausdorff, this hyperbolic Hausdorff dimension as the 0 of the pressure function. Okay, I will talk to this. So this is exactly, the pressure function is defined by such a formula. It can be proved that the limit really exists. And actually this pressure function is then the logarithm of the spectral radius of the operator LGT acting on the bounded continuous function of the space. And so this will help us, this formula will help us to estimate from above the Hausdorff dimension of the hyperbolic dimension of JL. So we proved really the following proposition. If W0 is a point with modulus bigger than R, then this value at 0 is finite if and only if the number t is bigger than 1. Moreover, if t bigger than 1, then the first displayed formula holds for G equal FL, this formula. Okay. And then if we fix t bigger than 1, then and t greater than or equal to R0. R0 was defined for these guys where actually we get good approximation between E, L, and FL. Then for every epsilon, there exists such number L epsilon RT greater than or equal to R. The quantifiers and dependence parameters really matters, such that then the kernel Frobenius is less than or equal to epsilon, okay, in such a uniform way. Okay, and so now, okay, having this, we have sufficiently strong estimates for the Hausdorff dimension of the model's function FL. I said we are ultimately interested in the function if L, so we have to actually infer similar properties for the functions EL from the functions FL. And since the functions FL approximate the model FL well enough, this was one slide before, we are actually in a situation which was considered by Volker Mayer and Anna Zdunik in 2021. And we follow to some extent approach of that paper. First, actually, and this is independently of this paper, we show that for sufficiently large R, the ratios in this domain, the ratios of the functions and derivatives are uniformly bounded with precise constants. Then, actually, okay, with this proposition, we can actually repeat the proof of proposition 7.4 in the paper of Volker and Anna, and to show that there exists a uniform constant such that we have for all L in C and R greater than or equal to R1, the ratio of transfer operator evaluated the function 1 is uniformly bounded. This is the key proposition. So then, okay, now having this proposition, we are almost ready with the proof. So first of all, as I already explained, is enough to show that limit if Hausdorff dimension, that hyperbolic dimension of the sets EL converges to 1. Okay, so fix t number 1, fix also any number r greater than r1, okay, which is large enough, for example, r equal r1. Then we have, in the previous slide, this slide, okay, with epsilon equal k to the power minus t, we get that this Hausdorff dimension is less than or equal to k minus t for all L so large and all W in W R star. So therefore, by this inequality, okay, this inequality will get that this transfer operator is less than or equal to 1. So and okay, and then this also holds okay, for all its iterates, and because this holds for all W in this disk. Okay, so then if you iterate, it holds for all iterates of this iterates, and therefore the supremum is less than or supremum is less than or equal to 1, and eventually the pressure is less than or equal to 0, less than or equal to 0. But this, the fact that the pressure is less than or equal to 0, this actually means, let's see, by this formula, Barański, and okay, we have it here, okay, this is less than, let's see, that this pressure is less than or equal to 0. So therefore, actually, if X, this could be a little bit simpler, but if X is any hyperbolic set in this in J of L, then topological pressure of a subset is always less than or equal than the topological pressure of the bigger set. So it is also less than or equal to 0. And therefore, okay, we need really the concept of hyperbolic pressure, okay, which is a generalization of hyperbolic dimension, also supremum over all hyperbolic sets. And Urbanski, Karpińska, and Zdunik proved that then actually the hyperbolic dimension in such a context is the infimum of such number S, where pressure of this function is less than or equal to 0. This really goes back to some similar results for so-called conformal iterated function systems. So therefore we get, since we already had that this pressure is less than or equal to 0, and okay, and so we get that Hausdorff dimension is less than or equal to T for all L greater than or equal to that. So the formula in our proof, so this one is actually established, and we are done. So this is the proof by a very concrete, actually, construction of particular functions, and the spectral gap in kind of strongest sense really holds. So, okay, thank you very much for the attention.
Yeah, thanks a lot. Let me start the discussion. Are there any comments or questions? Well, let's first thank the speaker. Yes, so are there any comments or questions?
Yes, yes.
Hi, I have a question. Are all of these Julia sets by any chance alphas regular, or in general, do we know things about other notions of dimensions for these Julia sets?
Okay. Yes. Let's see. So, okay, actually quite a lot is known. Okay. Let's see. Are you okay? They are regular. So, are you interested? I mean, the nice phenomena happen already for rational functions, and also very nice phenomena happen for let's see, for monomorphic functions. So, for example, for hyperbolic rational functions, okay, Hausdorff dimension, packing dimensions are equal, okay, and likewise for parabolic. But for example, for parabolic functions, usually, okay, and for hyperbolic rational functions, actually Hausdorff measure, and the exponent of Hausdorff dimension is actually up to constant equal to packing measure. For now, for parabolic functions, this is no longer true unless Hausdorff dimension of the Julia set is equal to 1. And if Hausdorff dimension of Julia set is equal to 1, then Hausdorff measure is finite and positive if Hausdorff dimension of the Julia set is bigger than 1, and packing the measure is infinite, while the packing measure is finite for if H is smaller than 1, for example, for some Blaschke products, then the packing measure is positive and finite, while Hausdorff measure is equal to 0. So now for meromorphic functions, for hyperbolic functions, there is also the concept of box dimension. And actually, box dimension, again, for hyperbolic functions, it is equal to the Hausdorff dimension, and this is simply so because for if you have hyperbolic rational functions, then the Julia set is actually the Hausdorff measure or conformal measure is alphos regular. So all possible dimensions actually are equal, except maybe Aswa dimension. And Aswa dimension was widely studied by Frazier from St. Petersburg, St. Andrews, providing actually formulas, especially for parabolic functions and some other rational functions, showing that they are really not equal to the Hausdorff dimension. In the meromorphic case, I think for, let's see, for exponential functions, I think parabolic, Hausdorff and packing dimensions are equal, although again, for exponential functions, hyperbolic Hausdorff measure is finite. Okay, is Hausdorff measure on horizontal strips is finite, is positive, is as a whole is actually let's see, sigma finite, while packing measure is let's see, is locally infinite at every point. Okay, so dimensions are equal, but Hausdorff, but these packing measures really differ. So then I think let's see. Okay, this was really I think Gwyneth Stallard and let's see, and Phil Ripon, and also the later Bishop, Chris Bishop provided examples, and maybe even Kirill Wajebnik and collaborators were packing dimension and Hausdorff dimension for various kind of meromorphic functions. They are different. Okay, I think that packing dimension and Hausdorff dimension are important because they are really purely geometric or geometric concepts, no dynamics involved, right? While these dynamical dimensions are actually kind of hybrid between dynamics and geometry. Right? They have also, all of them have merit, and the question of relations between them is really okay, always, by the way, packing dimension is greater than or equal than the Hausdorff dimension. So if the Hausdorff dimension is 2, then packing dimension is 2, right? So in our case, actually, it would be good question for our example, still whether packing dimension for this, which we provided here, is actually bigger than the Hausdorff dimension or not. I'm not really sure. Okay, but there is, I think, really good question whether there is even additional gap between this hyperbolic dimension, between let's see, between Hausdorff dimension and packing dimension. Okay, I don't know that, but this is, I think that this would be a really very good question further.
Yeah, thank you. I was actually thinking of the Aswad dimension because it's the largest one of them all, and I was going to ask about your example. You answered my question. Since the packing dimension, you don't know if it's equal. We don't know if it's equal to Hausdorff or not. Then the Aswad.
Right. I don't know. At least, okay. Maybe if one really even very studied Gwyneth's papers or so on, then could extract something. But I think this is good. I doubt, because I think when she wrote these papers, then still I think maybe this packing dimension was not so much studied back in 1990s.
Thank you so much.
You're welcome.
So are there other comments or questions?
Can I ask a question?
Yes.
Hello, Mariusz. So
Hi.
you showed that for the family you described, the hyperbolic dimension has a limit 1.
Yes.
But so do you have some concrete model, like a toy model, to get the dimension 1? What should I expect as this set, this hyperbolic set?
Oh, okay. Moment. Okay, let me put that way. All these examples of Gwyneth Stallard, right, have Hausdorff dimension really bigger than 1.
Mm-hmm.
And let's see. We really did not look at the what is the whether, okay, if you take the, well, you can get some limiting map for which the dimension would be 1. This would be actually the next question. This would be the biggest, okay, let's see, it still could, because these dimensions of these functions EL depend only on P, are the same for every L, right? Okay, let's see. These dimensions of this function EL are the same for every L fixing P. So maybe taking somehow L go to infinity, the dimension goes really to 1. So if there is some limit of these functions EL, or at least model functions, then probably, as you are right, but this would be candidate for having dimension equal to 1. And this would be even stronger dimension gap, right? If we can keep, still after this limit, if we can keep Hausdorff dimension to be also this 1 + 1 over 1 + P or something like that. Okay, I really don't know whether this limit, such a limit exists. I have not thought about it, but okay, you are welcome to do that. I think you are. So, and to see this will be the next, yes, also the next step in here to get even stronger gap, right?
Okay, thank you.
Yeah, yes, okay, welcome.
Okay, other comments or questions?
I maybe would like, let's see. I maybe would like to say there's something related that although for the this hyperbolic dimension we didn't get actually exact formula for the Hausdorff dimension, for the hyperbolic dimension, we only estimated it. We actually, for many classes of functions, with Volker Mayer, are able to provide exact formula for the Hausdorff dimension of points escaping to infinity. For large class of meromorphic functions in class B, for which infinity is not an asymptotic value. And then we have precise formula determined only by the behavior of actual multiplicities of poles. And maybe even play between this exact formula and so on, one could also obtain something. This is another paper with Volker Mayer. For the class of functions introduced by Weiler and Kotus, I believe in 2003 or so. So, and then there is so this is really quite exact formula. So this could be somehow could give maybe contribution to estimate altogether the Hausdorff dimension.